Hello everyone, my name is Said Kibarov. In this video we are going to present our term project, and other group members of our project are Dimitri and Caner. So in this project we are required to design a robot arm which will respond to the different angles which are entered through the program. Here you can see our implementation of the project. Basically we have used Arduino as a controller. Also we have used a low friction potentiometer, the DC motor, the robot arm with the weight on the one end. And this system is printed through the 3D printer in order to make the all components rigid, as a rigid body. Also we have the voltage controller which control the DC motor. It's a DC motor controller. While entering the desired angles in order to control the robot arm, here you can see the interface program. The desired angles are entered through here, so when we are entering the desired angle we can observe the response of the robot arms through this first window. Also we have these KP, KD, KI parameters, and by playing with these parameters we can observe the different responses of the robot arm. They are under-damped, over-damped and critical damped responses. So it's all for my part, and the other parts are going to be explained by other group members. Thank you.
Hello everyone, my name is Caner and I will show you the P and PD controller. First let me start with the P controller. Let me set the KP as 2, and here is the response of our system. As you can see, overshoot is nearly 0. It means that it's a critically damped response. However, if we increase KP, as you can see, there occurs a overshoot, which is not a good thing for the system. We need to set overshoot nearly 0 or 10. And I will increase the KP again, and our expect is increasing the overshoot. And yes, as you can see, overshoot is increased and settling times increased. Therefore we need to choose such that KP is 2 equal to, and so that overshoot is very small. Secondly, I will show the PD controller for you. I will set the KD as 0.65 and KP as 4. As you can see from the graph, overshoot is very small, and also the system is faster than P controller. It's a good thing for the system. However, if we increase KD too much, as you can see, the system becomes unstable, which is not a desirable situation. Therefore, we need to set KD as smaller values. Thank you, and here Dimitri will introduce you to PI and PID controller.
Hello, my name is Dimitri, and I will talk about the PI and PID controllers. So first of all, let's start with a simple proportional controller. As you can see, I have adjusted the KP parameter to 3, and we see a simple response of a P controller. Now we are adding the KI parameter. We're adding it to 5, and we can observe that the overshoot has increased, and also the system became more slowly, namely the settling time increased. Now let us pass to the PID controller. For the PID controller, first thing that we did was to tune our controller using the Ziegler-Nichols method. Ziegler-Nichols method says us that we have to find the least Kp value for which our system becomes undamped. Namely, it has constant oscillations. We have found that for our system, for the Kp value of 12, our system becomes as follows. As you can see, our system has constant oscillations. So we take this Kp value of 12, we also find the period of the oscillations, and we continue with the tuning of our controller. After all the required calculations, we came out with the values of Kp 7.2, Kd 0.38, and Ki 33.48. Now we can see what kind of PID controller did we tune. As you can see, the error is 0. Also, we found out that we have 2 oscillations. After that, we decided to play a little bit more with our system, and we changed the P controller. Actually, we decreased it from 7.2 to 5, and we observed that our system had a better performance. As you can see from the graph, we have just 1 oscillation, and also the overshoot decreased. So now we have a much better PID controller. Thank you.